This video is on how to rationalize the denominator when you have an expression containing surds. So before we even get started on how to rationalize the denominator, it's quite important that you understand some of those words I just said in terms of rationalize. You may not know what it means to rationalize yet, but you certainly know what a rational number is, or at least I hope you know what a rational number is. So what you need to know is when I say the word rational, or is a number rational, you should be able to tell me that any number that can be written as a fraction is rational. So for example, 2/3, that's a fraction. 0.3, that's 3/10, that's a fraction. So these are both rational. What else is rational? So any integer, any whole number can be written as a fraction. So all integers are rational. What else is rational? Root 16, that reduces to 4, which is the same as 4/1, which is a fraction. So that's rational. So then I guess we should think about, well, what's irrational? Well, certain surds that do not reduce, so basically all surds, are numbers that when you square root them, they don't reduce down to a nice integer. That would be irrational, so not rational. Okay. Another example would be something like root 3 or root 21. These are numbers that we can't square root down to an integer, so these would all be irrational. Put a little heading here. Irrational. Okay. And the numbers up here, we would say are rational. Okay. So what else would be rational? Well, the famous number pi. Okay, non-terminating, no patterns, can't be written as a fraction. Sometimes we see people write pi is equal to 22/7, but really that's just an approximation. So pi is definitely irrational, can't be written as a fraction. So what does it then mean to rationalize the denominator? Well, it means that your denominator must be rational. Okay, now, if you think about the denominator of a fraction, okay, if you think about the denominator, in the denominator, really, we only have place for an integer. So if you want the denominator to be rational, then the denominator has to be some sort of integer. So what does that mean? Well, you can't have a surd in the denominator. That's not a rational denominator. So when we talk about rationalizing the denominator, we want the denominator to end up with a nice whole integer. Okay, we can't have a surd in the denominator. So let's have a look at what a question would look like that asks you to rationalize the denominator. Here we've got 4 and root 10, and as you can see straight away, the denominator is irrational. It's a surd, it's root 10, and root 10 will not square root nicely. So that is irrational. What we want to do now is rationalize the denominator. And the process you're going to use to rationalize the denominator is multiplication. So the question is, what can you multiply root 10 by to get a nice whole integer? If you multiply root 10 by, say, 2, you'll get 2 root 10. And if you multiply it by any other number, that number will go in front of the root 10 sign, but will still be irrational. Hopefully you're remembering that if I take a surd and I multiply it by the exact same surd, then those two operations, it's like squaring the surd. And when we square a surd, the square and the square root are inverse operations and cancel each other out. So we end up with just 10. So really the only way to turn my root 10 into a rational number, or to rationalize the denominator, I would need to multiply by that surd again. Now you can't just go and change the value of this question. You can't just times by a root 10 on the denominator. So in order to do this legally, we want to also multiply by root 10 in the numerator. And if you think about it now, root 10 on root 10, well, that's just 1. So I'm not actually changing the value of 4 on root 10. Oops. It's still 4 on root 10 because really all I'm doing is multiplying by 1. So now we're ready to multiply. So I'm going to multiply 4 by root 10, and that will give me 4 root 10. And I'm going to multiply root 10 by root 10, and that gives me 10. And there you can see I have a rational denominator. I have rationalized the denominator. Now the reason why there's one more equal sign is you are expected to always reduce where possible. So I can simplify the 4/10 to 2 on 5, and just remember your root 10 as well. So I think hopefully that'll make it clear. Let's try a couple more examples. Here we want to rationalize the denominator. And so I've got a root 7 in the denominator. Now what a lot of students will do is they will multiply by 5 root 7, but I don't want to do that. 5 is not an issue to me. 5 is already rational. The issue is the root 7. So what I need to do is only multiply by root 7 so that I can get a rational denominator. Do not unnecessarily multiply by the 5. If something is already rational, then you don't have to really bother with that particular term. So here we've got root 7 times root 7 will give me 7, and when I multiply that by 5, I'll get 35. And then I can multiply my numerators as well, and the 3, well, that can go out the front, and the 2/3 will give me square root of 14. Okay. Once again, my denominator is rational, and if I have a little sticky beak, I can see that the 3 and the 35 will not reduce, so I'm done. Okay. Now, over here in this third example, we've got an interesting question where if I know my square numbers well, then I'll be able to tell that this actually reduces, both those thirds reduce. So I'm going to start first by reducing the 63 into root 9 and root 7, and the root 50 into root 25 and root 2. And when I do that, I'm actually going to get 3 root 7 on 5 root 2. Now, that's a problem because my denominator is irrational. So now that you've learned how to rationalize the denominator, you need to know that we expect you to rationalize the denominator in your final answer for all questions. We won't always tell you to. So we can see that my denominator contains root 2. So just like this example in this example over here, we're going to only multiply by the root 2 because the 5 is already rational. I don't have to worry about the 5. So when I multiply the denominator, I'm going to multiply the 2/3. The root 2's will give me 2, and then when I times by 5, I'll get 10, and then in the numerator, I'll get 3 root 14. And I can't see that anything can cancel, so that would be the end of that question. I definitely don't want to multiply by root 50 on root 50. That would have given me a lot of arithmetic, quite heavy. So the best way to start this question is to begin by reducing both your numerator and also your denominator. All right, let's look at one more question that steps it up a notch. Okay. Once again, we want a rational denominator. So here I can see that my denominator is not rational because it contains a root 3. So I'm going to multiply by root 3, and whatever I do to the bottom, I'll also do to the top so that I'm actually not changing the size of this expression. I'm really just multiplying by 1. Now, let's do it. The only difference with this question to the questions in the previous slide is these questions in this slide, there's only one term in the numerator, and with this question, there's actually 2 terms, 1 and 2 terms there. So when you multiply your root 3, you're actually going to be doing root 3 multiplied by both of those terms, and there's a good idea is to write it out like this first. Okay, you definitely don't want to do too much in your head and then make mistakes. Now on the bottom, let's multiply the root 3's. That gives me 3, and then I'll times by 2, gives me 6. From there, I can now expand my brackets. So if I expand my brackets, I get 3 root 3 minus 6 root 15, all on 6. Now, it looks like that's where you stop, but this is actually a really good question, because it turns out we have we can actually reduce this expression further, and you are expected to go that extra mile. So what you could do to reduce it, there's 2 different ways of thinking about it. You could take out the 3, and that would give you root 3 minus 2 root 15, because you can see that this 3 and this 2 will multiply to give the 6 that's there. So just check it visually. You can see 3 times root 3 is 3 root 3, and 3 times 2 root 15 is minus 6 root 15, all over 6. And then hopefully you notice that the 3 is joined to the bracket by times, and we can multiply across a multiplication sign. So now I can cancel this 3 with this 6 2 times, and so really my final answer would be root 3 minus 2 root 15 all over 2. And that is fully simplified. That's one way. I quite like that as a method. The other way, if you feel like your maths is quite strong, is you can actually divide all the terms by 3. And the only time you can do that is if you have a common factor to all 3 terms. If the factor isn't common to all 3 terms, you can't use this method. So I can see that 3 goes into all 3 circle terms, so I'm going to divide them all by 3. If I divide this first term by 3, I get root 3. If I divide this term by 3, I get 2 root 15. And if I divide the denominator by 3, I'll get 2. and it produces the exact same result that I got before. So it doesn't matter really which method you want to use. Either, I think, are both fine, just as long as you understand them, understand exactly what I'm doing in both. All right, that's all.